Okay, so let's just have a quick look at the result for this heat map. So we can see that we've got our dog annotation in the top row, and those are the colors that we chose with the hash codes here. You'll see we didn't choose colors in this case for treatment. We could have. Normally you would like to probably customize your colors. If you don't, R will assign its own colors. So in this case you can see it's got like pinks and purples, and they're all very similar. So it's not really easy to distinguish between those treatment categories. So it's better to go choose your own colors for that. So then at the bottom we've got our dog annotation, and you'll see that there's also clustering performed on the taxa, in addition to the clustering that we performed by samples. So we don't see the hierarchical clustering tree at the top, but nevertheless the samples have been clustered with our Bray-Curtis distance using that hclust function. So that heat map will appear for us here in the plot, and if you go to your Files tab, you should also see it in your R downstream directory as that heat map merge taxa.pdf. Another nice exploratory plot that I'd like to show you guys is the bar plot. And again, the bar.plots function is a custom function that I've built around the functionality available in Phyloseek. And I've done that so that we can have a nice filter so that we can limit the number of taxa that we have in our figure legend, so the figure legend is not crowded. In the microbiome custom functions tutorial file, we can have a look at the bar.plots function, and that gives you a nice generic bar plot that's built around Phyloseek's plot bar function. So let's have a look at the actual code and the arguments that you should specify. Again, your Phyloseek object with your standardized counts, and then we can make separate bar plots by a category of interest. So in our case, we might be interested in creating a bar plot per dog, so we can see what the kind of proportion of taxa are per dog. And then the level you specify is at what level that you would like to perform your merging, genus level, family level, and so on. And then there are two filtering parameters to specify. This perk is a minimum fraction of samples which should be positive for a given taxa to minimize that taxa in your figure legend. Then the count is the minimum per taxon count summed across all samples. So that perk and count, you would need to play around with that for your own data set to figure out what is a acceptable level for your data and regarding the number of taxa that you would like to display. And then you can also subset by OTUs and samples, just as for your heat map, and then you would specify your file name. So let's give that a try. So we give it our standardized object, and in this case we're going to select dog as our category of interest. The level that we're going to merge at here is at genus level. And for now, let's just specify count 500 and percentage 0.25. So that means that we want at least 500 counts in at least a quarter of our samples. You can specify your output directory. So we can just make that our working directory. And we give it a file name. So we can run that, and that will save your plot as a file. So we see here the bar plots by dog genus abundance, and it'll also create, if you use print bar plot for that object, it'll show you the plot over here. And then it also gives you the ends here at the top, so that's the number of samples per category. In this case, we've got 5 samples for each of our dogs. So we've got dog K, G, and B. And then here we've got the genera that were included in this plot. So obviously we've got a lot more genera available in this data set, but here we just summarize the most abundant ones. Otherwise, you'll have a figure legend with maybe 50 entries and it becomes illegible. So the way this customize function works is to summarize for us by category, and say for dog K, it does that by taking the median value of each of our genera, and then it summarizes as the percentage of sequences for that category. Just to show you guys as an example of maybe when you want to build your own customized functions, why this function was built in the first place. So it was based around the plot_bar function from Fileseek. So let's see what happens if we use only this function in Fileseek. So we're going to specify a Fileseek object, and then we're going to specify our category of interest and the level for our legend. So I'm going to make it by dog, and I'm going to make full genus. Okay. If we look at the plot section, then here, so that's what I mentioned, where you've got so many different genera that the figure legend becomes entirely unusable. So if we export this and save it as a PDF, we can go have a look at this file. And now you can see here it's separated by dog, but this is really not very useful. We've got this massive figure legend here, and it hasn't been summarized as a percentage of your counts. And so that is why we went and customized that function, so that instead you can have something that looks more like this. And that's a nice, easy summary for the user to get a quick overview of the dataset. So we now move on to the final section of our R downstream analysis, which is differential abundance testing. So we've seen now from our data from the beta diversity analysis and the heat map that we expect certain differences in microbiome composition between our dogs. And now we'd like to figure out which taxa are actually significantly differentially abundant between these dogs. And for that we can use differential abundance testing. So for our 16S data, which we've discussed as compositional data, that has a zero inflated nature, a suitable method should consider this structure and also differences in sampling depth between our samples. So we could use something like a non-parametric test, so we don't have to worry about that specific distribution. So we could use Wilcox and Ranksum or Kruskal-Wallis, but there are actually more powerful parametric alternatives such as DSEG2 and EdgeR, which are R packages that were originally designed for RNA-seq data, and both fit generalized linear models and assume the read counts follow a negative binomial distribution, and they primarily differ in the way that the normalization between samples is achieved. So the negative binomial model does not fit data that well when we have a lot of zeros, which we often find in 16S data where several samples may not have that taxa at all, and it just occurs in a few of your samples. So to address this, we have a package called Genomeseek, which applies a zero inflated Gaussian model. So it was specifically designed for this type of count data with variable coverage between samples in mind. So Genomeseek, in addition to this generalized linear model where you test for differences in abundance, also employs Fisher's exact test to test for differences in presence and absence between your two groups of interest. Let's see how these different methods perform if we compare them, and there have been several studies that look at their performance. So here we've got an area under the curve plot which looks at false positive rate and true positive rate, and an area under the curve of 1 would be perfect performance, and 0.5 would be pretty much random. On the right, we have median library size, so either 2,000 or 50,000. And then they've also gone and compared different samples per class, so 3 versus 3, 5 versus 5, or 10 versus 10, which are the different shaded lines here. And if we look at how Genomeseek performs compared to something like EdgeR and Dissect2, if you've got a decent sample size, maybe like 10, they kind of all perform similarly well. Maybe Genomeseek performs slightly better at lower effect sizes. But if you've got a low sample number, like 3, Genomeseek doesn't perform that well. And we'll see in our tutorial how we can improve this a little bit by filtering the results from our statistical test based on presence and absence data. So if we look at the bottom here, we can see specificity and sensitivity measures as well. And here we can also see that compared to the other methods, Genomeseek often has slightly more false positive rates than the other methods. And again, with filtering, we can improve this. So in general, I think Dissect, EdgeR, and Genomeseek are all really good methods to use with your data. If you're interested, you can run all 3 of them and see how they compare. And always just have a look at the output in a visual format like a heat map, which we're going to be doing as well downstream, to see that the results make sense and that you're not maybe getting positive hits that are driven by outliers in your data. For instance, for a given ASV, one group might have no hits, while the other group has a very small fraction, but with high abundance positive hits. This may result in significant p-value, and these results should be filtered out, and we'll see how we do that downstream as well. Genomeseek uses a normalization method that accounts for differences in sampling depth called cumulative sum scaling. So these scaling factors are included in the generalized linear model, which computes the probability of zeros due to either low sampling depth, where the ASV might be present in reality but not detected by sequencing, or sparsity, where the ASV is truly absent. So in Genomeseek, we can also include covariates, which is great if you have a confounding factor that you'd like to account for in your study. And then, as I've mentioned, the results that we get from the Genomeseek testing do require filtering based on ASV presence to avoid false positives, especially if we have a small sample size. So from the Genomeseek guide, they do give you a warning here. So the user should restrict significant features to those with a minimum number of positive samples. What this means is that one should not claim features are significant unless the effective number of samples is above a particular percentage. So we'll have a look at that and see how we'll do that in our downstream. So let's head over there. For further reading, you can click on this link, and that'll give you more information on Genomeseek. You'll find a video presentation by the author that you can go through if you're interested in more of the theory.